Depends on if you're the teacher.
Let's backtrack there. If you're the teacher, so feel free at any point to be like, I did not know that content. And for those of you being like, well, that wasn't work, we are changing structures as we go through this.
And this should really be a review, right? Like
Last one is.
Theoretically.
yeah, like this is supposed to be a review.
Why should it be a review? Play pause it and the reading and the lecture you guys all practiced last week. Have I named any of them yet? Yes, I did. I named one of them. I always get this one wrong. I don't know if I should include the A or not.
I didn't put that. I don't believe so.
I think it's just possible.
From what my understanding.
According to my recording, it's been 1 minute and 47 seconds.
Probably done faster on the paper.
So when I asked that question about that last one, that's what you had in your head, right? Totally. Oh my gosh.
I'm timing you. You're at 3 minutes.
2.5 minutes. Every single one of them is solved with work.
And color coding. Like, that throws me off.
Okay. Yes, I am the teacher. So that one, I go, oh, you're the teacher. Yes, I also wrote everything down. This is the most common complaint you will hear through the entire semester. Write it down. If you don't write it down, you will get it wrong. When? Maybe not all of the time. Maybe 60% of the time. Okay? I have a problem with you getting it wrong 60% of the time. Okay? You theoretically should too. Okay? The idea is to come up with a system that allows you to consistently achieve the answer by showing all of those steps and those processes along the way. Okay? For homework, color coding this works great. I'd fully accept that. Okay? If you don't have it color coded, you could go through and say, well, this die comes from that 2. This pent comes from that 5. You're now showing using a notation, admittedly not the English language, but you're creating a language system that allows me to track how you came up with that information. More importantly, you came up with a language system that allowed what? For you to study. You now can look at it and be like, that's why I did that. If you don't provide that work and you just say the answer is E, you have nothing to study from. You have no way to frame a reference to go forwards. You need to be writing out work behind this. Kind of, sort of? Yes?
This is kind of just for me, but for the lead one, can you write like the right answer just in one color?
Yep. So it is PB, C2, H3, O2, 4.
That's simple.
That's it. Okay? This also becomes one of the challenging things. You have a problem with nomenclature, you go to the tutoring center and you say, I'm having a hard time solving this. So like, oh, it's just PB parentheses C2H3O2 parentheses 4. Where the F did you get that information from? Same thing happens with Lewis structure. Okay? You don't see the process behind how they're doing it. All of that work, when someone immediately jumps to what's in blue there, the PB, the thing that Kendall had me write out, okay? They did all of that work in their head. Okay? And again, I really don't necessarily have a problem with you doing work in your head. Where I do have a problem is you doing work in your head wrong. Okay? That's the issue. And if you don't spend the time to write that information down as you go through and do your problem solves, okay, you don't see where you're doing it wrong. So you may get to the end and say, well, the answer I came up with was PB4C2H3O2. You go to the back of the book, you look up the answer, and it says it's PB that. Okay? What happens? You go, oh, I just put the 4 in the wrong spot. No, you didn't. You had an entirely massive misconception behind how and why it was supposed to function the way it was, and all you've done is reinforced your misconception. That wasn't just a misplacement of the 4. Your reasoning behind it was fundamentally flawed. This is why I don't give you answers to the practice exams. Right? Because what will happen is you'll look, oh, I said it was C, but it's B. Because clearly, you're just supposed to do a line with 2 humps next to it. That's not how you solve a test. Okay? So be very careful when looking up answers. I understand the need to verify that you are correct. That's absolutely fair game. Just be aware there are huge issues with that. If you are wrong, that does not mean you're done. That means you have 4 more questions that you need to go and get correct. Okay? Because you have a misconception, you have to find 4 more questions to see if it's actually a misconception or if something else is happening. Okay? Kind of, sort of?
You have to take time to diagnose what's going on, and you can't do that in your brain.
Okay? For instance, would anybody be okay if I just put a mind-reading device on you and said, I'm just going to read your mind for the next hour? Is anybody going to be like, cool, that's fine?
No.
Why the hell not? Because your brain is a freaky, scary, nasty place to be. Right? Don't be doing your work in your head. Okay? Because that freaky, scary stuff is going to mess with all the work. Put it on the paper, not the freaky, scary stuff for the record. Right? Yeah.
What? I have in my notes that the acetate ion has a negative charge. I'm wondering why there isn't one.
Does the acetate ion have a -1 charge? Yes. Is that information specified in my work? Yes. Where was it specified? Okay. Admittedly, I did F up my work there, because there's the charge on the acetate. What was the Y? 4. It eventually became the 4. What was the meaning of that Y? It was the number of acetates that needed to go into the formula. So I did charge times number. What did I do for the lead? Charge. Oh, no, actually, I did it right. Cool, look at that. Fantastic. Times the number of the lead. Okay? The more consistent you can get behind that pattern, the better off you are. Okay? We now have 2 questions about the lead acetate, so I'm going to guess you would like a slight poking at the lead acetate. Yeah, let's poke at it. Okay? The other thing that I noticed walking around is there was some struggling with the CR203, so we're going to poke at that one too. Most people got the middle 2 right. Okay? So we're not going to poke at those too hard, but we are going to address those.
It does make me feel good about what we did last Thursday.
So when we go through and look at these, what do the middle 2 have in common? What do the outer 2 have in common?
The
The inner two are easier. Yeah? Why are they easier? The bond for the inner two is different than the bond for the outer two. In one case, we have cations and anions, and we would know that because what kind of connection do we have between a chromium and an oxygen? It's an ionic. How do we know it's an ionic bond? It's a metal and a nonmetal. Was that content in Unit 1? Yeah. Fascinating. Okay. How do we know it was a metal? By looking at the periodic table and recognizing where it is with regard to that staircase. So that simple stuff that we talked about, there was, we don't need to know that. Yeah, we do. Okay? That's how we classify these things. That's what allows us to differentiate. So in the middle two, the bond connectivity is a covalent bond. Because they're nonmetals. The outer two are ionic bonds. Why would I call them different things? Ionic versus covalent. Tricarbon dioxide is different from N2O5, is it not? Okay. Why is ionic being called different than covalent? I don't accept just that they are different.
One, you have to worry about it.
There's getting an idea. In the ionic, we have to worry about these charges. You mean the chemical reactivity is different between these two types of bonds? Yes. So it's a slight nuance off of just saying they're different. Address that aspect of why they're different. So the chemical difference is there. Okay? That's why we call them ionic versus covalent. Okay? But as soon as I go through and call it the name for each of those compounds, I lose the context that it's ionic unless I have to go back to the periodic table. Oh, chromium, metal, oxygen, that was ionic. I wonder if there was a way that when I write out the name, I can identify very quickly what kind of bond is there without having to go to the periodic table. There is. Take a look at the top or the bottom two. What's the difference between those names? Roman numerals versus prefixes. Guess when you use prefixes? Covalent compounds. The instant you see a prefix, you know the bond connectivity. You don't have to look at the periodic table to evaluate metal versus nonmetal. We created a nomenclature system that allows us to find that information kind of as a second nature aspect. That's a pretty neat system to build. Same deal. If you see Roman numerals, that's now a giant red flag that you're looking at. An ionic bond. We used a different rule system so that we could differentiate those compounds at the name level. That's pretty cool.
There's no exception to those rules, right?
True. Let's just go with true.
Do you guys see the logic behind that language?
Right. So that's kind of neat. Right. So our covalent ones will use the Greek prefixes to specify the amounts. When we go through to get the names for ionic compounds, the amounts aren't specified. Okay. And that is a big shift in the nomenclature system. Okay. That's what allows us to differentiate ionic versus covalent. The problem with that is that we now have to come up with a way to figure out the amounts. Because when I look at lead-4 acetate, I need to know how much lead is there, how much acetate is there. Right? My name has to somehow give me some of that information. Okay? That information is encoded in a slightly different fashion. So let's take a look at the lead acetate. So we'll break it down. We know lead has a symbol of Pb. Acetate, we know, is a symbol as C2H3O2. How did you know lead had a symbol of Pb? Told you to memorize it. There is some content you have to memorize. You have to know the letters of the alphabet, right? Right? How did you know acetate was C2H3O2? for the exact same reason that you know lead. You have to memorize it. In that nomenclature video, I told you there were 7? Was it really 7? Since you're pulling up your notes, hopefully you can help me out with which 7 there. All right, let's not do that because I don't want to write them all out. Okay? There are 7 that you need to memorize. Acetate is one of them. If we look at the list of polyatomic ions, there's a whole lot more than 7. Why am I telling you to only memorize 7? We could say I'm nice. That's way over generous. Way over generous. You just saw your exam. Okay. Why only 7? Those are the 7 you're going to see most commonly. It makes no sense to memorize useless information. Okay? I don't have you memorize the F elements because we don't use them. Same thing. With our polyatomic ions, we need to memorize certain ones. Okay? Which brings in the next part. We need to know how to put these together. Well, because it's an ionic compound, I know these things are charged. Because I know something about electronegativities, my metals carry a positive charge. Well, how positive is it? Is that like positive, I got a 60 on the exam? Is that a positive, I got an 80 on the exam? Is that a positive that I got 100 on the exam? Because I'm pretty sure those positives are different, right? Okay. We could even get a positive, I got a 40 on the exam. Okay, and you laugh, but if your expectation was to get a 0, a 40 is pretty freaking fantastic. Okay? How do I know what its positive is? That's what the Roman numeral's for. The Roman numeral tells you the charge. Okay? We won't always see a Roman numeral. When do we see Roman numerals? Okay? I like it. You're coming up with some ideas. Ionic compounds. Cool. Sodium chloride. Ionic or covalent? Sodium is to the left of the staircase. Chlorine is to the right of the staircase. That would be a metal and a nonmetal, which would make that ionic. We actually said the name out loud. It was sodium chloride. In the process of me saying that out loud, did you hear me say the Roman numeral? No. Should you write the Roman numeral? No. Okay. It's an ionic compound. Why should we not write the Roman numeral for sodium? It is absolutely a +1. It is absolutely balanced. That formula is spot on perfect. That name is spot on perfect. Why do we not specify the Roman numeral?
Because it has a negative one and a positive one.
Lead 4 acetate. When I change the amount, I can balance it out to get 1 lead and 4 acetates. It balances out. Same argument would apply. I shouldn't have to show the 4. Okay, I apologize. So let's switch to a different question because that one is challenging. What is the ionic charge for fluorine? -1. Oxygen. -2. Phosphorus. -3. Aluminum. +3. Strontium. Sodium. You said that awfully fast. What charge is sodium? +1. When? Always. Because it is always +1. When I put it into a compound, what is its charge? +1. We don't write redundant information. Sometimes. Right? This becomes tricky because you could go, well, I'm going to write the 1 just to be clear that that charge is 1. Okay? What was my name? Mike, full name? Mike McFadden. Is it Mike McFadden 1? No. Yeah, I'm the first one. There is no other Mike McFadden. Yeah, it's Mike McFadden 1. Okay? Would you ever add that 1? Okay. If I had a kid, I wouldn't name him 1. I would name him 2. Right? Why do we not add the 1? That was redundant information. Okay, as I quickly think about everybody's name in the roster, I think we're all 1, or do we have a couple 2s? Damn it. Okay, most of us are 1s, some of us are 2s. Okay, so at least 2 people, because really just 2 people? I just saw 2 floating hands. Well, that's kind of cool. 2 peoples are 2s. The rest of you should have 1s at the end of your name. Beside the point. Okay. We don't specify the 1 because that's extra information. When it comes to chemistry, we do ultimately the same thing. That's extra information that is not required to be part of the name. Okay. So should we be going around and telling, well, my name is Michael McFavelin 1? Okay, I'd get looked at kind of weird, right? The sociocultural norm says, don't do that. Who invented the sociocultural norm for this? Chemists. A group of chemists and physicists got together to come up with a standardized system for naming chemicals across the world so that we would not be confused. Within that, they established certain rules. One of those rules is don't specify charges for elements that only have 1 charge. The instant you do, guess what? You're wrong. You are breaking the sociocultural norm, and you get marked incorrectly. Okay? Which means when we write out sodium chloride, we are not allowed to show the 1. So the Roman numeral shows up in ionic compounds when we don't know the charge, because we need to clarify it. Why does it not show up with the other ones? Because I'm supposed to know the charge. Is there some information that you're supposed to know in this class? What was lead? PB, yeah. Okay. Did someone tell you that you're supposed to know the charge on sodium? Yeah, I did. Okay. I believe it might have even been on the test. Yes, I told you you're supposed to know that charge. There are certain elements you are required to know the charge on. For those elements, they never show the Roman numeral. Okay? For the other elements, we have to specify it. Why? Because I have to know how many lead needs to balance the acetate. In the case of the sodium chloride, it becomes really easy because the charge on sodium is a +1. The charge on the chloride is -1. Okay? We started to see this formula show up, and you might be like, well, where did that come from? It was in the video. You may not have liked it. That's a whole other issue. Okay? We're creating this formula. The charge times the number of that element, how many are there, plus the charge on the next element times the number of how many must equal the overall charge. As far as nomenclature is concerned, it is 0. Okay? So what do x and y have to be for this equation to be true? It could be 0, in which case do we have sodium chloride? We'd have Na0Cl0. For those of you being like, well, yeah, why not? Okay? So let's specify sodium chloride. It is Na0Cl0. That would mean there's 0 of each of those, right? Which means for every compound, oh, Lord, yeah. Yeah, that's not going to be fun. When it's 0, we just ignore it, delete it, don't write it. Okay? We were able to do that math relatively quickly in our head. What I'm trying to show by that formula is that that's what you're attempting to do. You're trying to come up with an expression that allows you to solve those things. Most of the ones that you're solving are relatively straightforward. 1 into 1. Well, I just need 1 of each. Ultimately, you're guessing at a solution. Somebody said 0. Is 0 a valid answer to this? 0 times 1 is? Might or plus -1 times 0? 0. So 0 plus 0 is? 0. Is that a valid answer? Yeah. Does it satisfy the original question? No. Okay. We would have to get a number greater than 0 to satisfy our original question. Okay? So let's pull this information back down to our lead acetate. The lead we said was a +4 because
It says so.
it says so. That's what the Roman numeral is. The acetate is what charge? -1. How do we know it's a -1? You were asked to memorize it. Just like for sodium, you were asked to memorize that sodium is a +1. For acetate, you're required to know acetate is C2H3O2 and it has a -1 charge. Those are pieces that you have to know to be able to continue the process. Okay? Those two things need to somehow balance out. Okay, so let's break this down. We got our x, y, 0. Just like up here, we could just start guessing. You guys were able to plug in ones really quickly to see that that's solved. You might not be able to plug something in here all that quickly. What number could it be? 1, 2, 3, 4, 5, 50 billion. All of those are perfectly valid entries. When we're building a formula, what numbers do we want to use? The smallest possible. Okay? Why the smallest possible? Because what we're trying to do is represent the smallest possible unit for that compound. So I want to use the smallest numbers possible. So in the work that I set up, what did I do? You notice I had a question. I was kind of cheating. What was my question? Because I'm going to guess. What am I going to guess? X equals 1. If I guess x equals 1, 4 times x is 4. Minus y, I've now distributed the charge, has to equal 0. Yeah? Now I solve for y. Y equals +4. Did I have to guess x was equal to 2? Or sorry, the other number that's there, 1. No, I could have guessed anything. Right? I just picked a small whole number first to try and get this figured out. Okay, to get me a starting place. What happens if instead of guessing x, I guessed y? Guess y equals, you're all saying 4. You know the answer though. Thank you, Dane. 1. 4x minus minus 1 equals 0. 4x equals 1. X equals 1/4. What does that mean? My guess sucked. Try again. Okay? It's literally just a guess. We're just trying. Forcing it in there to see what happens. Because our numbers are low enough, we can run through these guesses pretty quickly. With enough practice, what do? You internalize that process and you don't have to write it down anymore. That's fantastic. That's good with practice. Don't practice it. You're just guessing right out of the gate. That's where it becomes problematic. So far, so good? Is there another way we could represent it? Of course, there always is. Lead. Ta-da! That's what lead looks like. Fancy little circle. What charge was it? +4, right? So 1, 2, 3, 4. Guess what acetate looks like? Ta-da! Acetate. What was its charge? -1. If I bring one acetate and one lead together, what happens? Those charges cancel. Would I have an overall neutral compound? What do I need to do? I need another acetate. Charges cancel. Is it neutral yet? Nope. So what do I do? Another acetate. Charges cancel. Another one. Charges cancel. How many leads did I show? How many acetates did I show? Actually, let's switch this up. What was our symbol for lead? Don't tell me a red circle. Pb. Our symbol for acetate. C2H3O2. So our formula is PbC2H3O24. This is why we include parentheses.
Why?
to disambiguate that information. Okay? The same process worked down here. Remember when we guessed x was 1? What did we say x was in our formula? Don't tell me 1. The number of something. Good start. Somebody help her out. The number of lead. When I went through and solved that, I got y was equal to 4. What did I say y was? Don't tell me 4. The number of acetates. I can now add that information in. For those of you that were looking really, really fast at how I worked, you can rewind back to roughly minute 1:45. You saw the 1 show up next to the lead, and then fairly swiftly afterwards, whoops, what happened to it? I erased it. Why? It's that extra information. I don't want to write in 1s because I've already specified that I had it by writing PB. Okay? Exciting. Yeah? What do we got, Dane?
What's the name of that method that you just showed us? The
Picture method?
Remember when you talked about representations and models, right? We talked about that last week.
Yeah, I don't know. Honestly, I don't like that method, and I'm starting to like it more and more because it helps get beyond the kind of mathematics. I'm definitely a math-centered mind, and so I see that a lot easier than I see the shapes.
That reminded me of Lewis structures, though.
Don't do that. Okay, that's a really bad connection to make. Don't do that.
So, I feel like that picture method would only work if there's only 2 different things in the bond.
So there's an interesting question. The picture method would only work if there's only 2 different things in our bond. Okay? As opposed to this method that has 2 different things in our system. When we're looking at our structures, we're really only looking at 2 different things coming together. Okay? Some of those will be more complex, like acetate. Acetate is one thing with multiple pieces. Right?
All the 7 polyatomic ones that you wanted us to memorize,
Yeah.
do we have to memorize the charges? for
Yes.
those 2?
For those 7, you need to memorize the charges because we got questions on it. Oh, let's see how I can do. So we've got acetate, we have sulfate, we have hydroxide, that's a -2. We have nitrate, we have carbonate. Cyanide? Should I say cyanide? 6. I don't know what else I told you to memorize.
David.
Acetate, carbonate ion, cyanide ion, hydroxide ion, nitrate, and sulfate.
That's only 6. Hydrogen sulfate. Yeah, that one's not that big of a deal, but it's there. Hydrogen sulfate.
When they're memorizing this, that's actually, there's more to it, right? They memorize that, but that's like the base, and then it can go up or down, like sulfate versus sulfite.
Sulfate versus sulfite, I cannot stress this enough, is a horrible, horrible system as well. Okay? I hate that reference. I understand why people want to point that out, but the only reason that is valuable is because you have something memorized. Okay? If you don't have something memorized, sulfate and sulfite or ate and ite are meaningless. Okay? So you had to memorize something on which to hang that. So you're memorizing sulfate is SO4 -2. Oh, and I can hang on that 8 means more and ite means less, so sulfite is SO3 -2. You mean you memorize 2 facts, or you memorize 2 facts? How about we just memorize them outright without having to memorize an extra complicated step that gets overemphasized? For instance, sulfate has how many oxygens? 4. Carbonate has how many oxygens? 3. Isn't 3 less than 4? Yeah. Why is the system changed? Because it's a different freaking compound. The rule of 8 versus ite is a bad connection to make. I understand the parallel that's there. It's not worth memorizing. Okay? Because it does not apply consistently. Okay? You had to memorize too much information outside of that. Okay? Also, what do we end up with if we say 8 versus 8? We'll end up with acetate. What the hell is that? Good question. I have no clue. It doesn't exist. Okay? So don't make that connection between 8 and 8. I know it's there. It's too easy to overuse. And that's the problem with it. Okay? Chromium oxide. Should we look at that now?
Yeah.
Okay? Because now we're flipping it, right? We're reversing the process. Actually, I don't want to delete everything, just in case I want it up there. So, when I went through and solved it, what did we see right away? I wrote chromium, then I wrote oxygen, and then, because we're looking at a compound, we changed the ending to "ide." Okay? This one is one that we'll point out here in a little bit. Okay, so we've named the individual pieces. Is chromium one of the ones you're required to know the charge on? And you're like, well, I don't know. I didn't memorize them. Exactly the problem. Okay, so we do need to memorize those. Those can be memorized for just long enough to write them on the exam. And we'll notice that chromium is not group 1, group 2, zinc, cadmium, silver, or aluminum. Which means you need to specify it with a Roman numeral. It's not one that you got memorized. Okay? How do we figure out what its charge actually is? Okay? This is where I don't like that circle thing, because I've got this chromium. I could argue. I'm going to try it. I'm going to try it. I'm going to try the circle thing. I'm not going to like it. I don't have to like it if it works, right? There's the chromium. How many chromiums do I have? 2. And then I have the oxygen. 1, 2, 3. What's the charge on the oxygen? Oh, this is going to be painful. Oxygen you're required to memorize is -2. Each of those, negative, 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 negative. Sorry, I made them too big to put them inside. Okay, so minimally the chromium needs a positive, so it can cancel that one, right? I need a positive, so it could cancel that one. I kind of hate to friggin' admit it.
To admit what?
It works.
Just gets a little messy.
So 6, careful. There's 6 total positive charge spread across 2 chromiums. What's the charge on an individual chromium? 1, 2, 3. I can't believe that friggin' worked. The problem I've got with that is that's a lot of like drawing and checking and crossing. You'll notice that I also had a pattern behind it. For every positive, I tried to balance them. Because I could have just put all of the positives in one of them, but then no positives there. That would mean 2 different chromiums. They have to be the same chromium. Okay? So there kind of had to be a balance there. Right? If it works, it works. Okay, kind of. Okay, so and the reason I'm erasing that is I want to show that the other method also works. Okay? In that method, what do we say? We want charge first. Well, do I know the charge on chromium? Don't tell me +3. We just solved that. So don't know that. So we don't know it. It's X. How many chromiums are there? 2. Times 2 plus. Do we know the charge on the oxygen?
Yeah, -2.
We know the oxygen's a -2. Do we know how many oxygens there are?
Yes, 3.
There's 3. This equals
0.
0. How do I know it equals 0? I'll accept 2 answers. It has to. It has to right now, because we said when we do nomenclature, it has to be 0.
Because it doesn't specify.
Where is charge specified?
Top right.
The upper right-hand corner of our formula. Is there anything written there?
No.
Why?
0.
Because it's 0. Okay? That will come back and haunt us when we look at chapter 17.
What's the other answer you would have accepted?
We just addressed it. Upper right-hand corner, and no, we're not responsible for, or it's always 0. So we get 2x minus 6 equals 0. 2x equals 6, x equals 3. Look at that. It came out to the exact same thing. Yeah.
Forward, can we do either or method?
Yeah.
Oh, cool.
Yep. I do want to say there are other methods out there that I'm very hesitant to discuss. The textbook talks about them. If you hear a reference to the crossover method, it's a very dangerous method to use because it removes your understanding of what's happening. We're putting the compounds together to balance that charge. Both of these methods that we've shown show that that's the focus, balancing the charge. What's the crossover method? Well, I just cross stuff around and numbers work. So you have no clue what's going on. The instant we move forward where you actually have to understand how to balance charge, you don't have a process to solve. So I do not recommend the crossover method because it removes chemistry understanding. The important part of nomenclature is not the name or the formula. The important part of nomenclature is the process of balancing those charges. That becomes the important part. That's all the work. I could really care less that you know chromium is CR. Or, for most of you that wrote it down, that chromium is spelled C-H-R. Okay? So with that, unfortunately, we got to be done. There were a couple questions in the back. I'll go back and talk to you guys.